Chancellor of lovely Professional University, Sri Ashok Mittalji, my colleague, and the General President-elect of the Indian Science Congress Association, Professor Vijayalakshmi Saxena, Professor Belmont, the wife of the Nobel Laureate sitting in the audience, the Pro-Chancellor of LPU, Mrs. Rashmi Mittal, Professor Ashok Saxena, other distinguished members in the audience, the young and bright students with the glittering eyes and hungry for knowledge sitting here. I extend a warm welcome to the Nobel Laureate Professor Duncan Haldane. I deem it a great honor and a privilege to chair this session. Let's give a warm welcome to Professor Duncan Haldane. Your clap should be audible to Nobel, who instituted the Nobel Prize. और जोर से ताली बजाओ. ये तो ऑन है ना? Professor Haldane is presently working at Princeton University and is developing a new geometric description of the fractional quantum Hall effect that introduces the shape of the composite boson. I hope the youngsters present here are aware of boson. Different states of condensed matter, solids and liquids were classified for a long time in terms of their symmetries. The 2016 Nobel Prize in Physics was awarded to Professor Haldane for his independent and illustrious work that has led to a paradigm transition between states of matter because they are topologically distinct. Professor Thors Hansen, a member of the Nobel Committee in Physics, said the Nobel laureate, Professor Haldane's work, combined beautiful mathematics and profound physics insights and achieved unexpected results that have been confirmed by the experiments. That shows the outstanding work that Professor Haldane has contributed to the scientific world. Professor Haldane, sir, the youngsters present here, as I said, are hungry for knowledge, and all of them want to excel in their careers, whichever they choose. This country has about 700 million youngsters below the age of 25 years. No other country in the world has such young intellectual potential. That's the greatness of this country, and the government of India and other state governments do provide opportunities for all these youngsters to get educated and contribute to the society. The government has started several premier institutes in private as well as public sector. The country provides conducive environment for creative thinking by all these youngsters. I'm sure Professor Haldane will excite and motivate the youngsters to choose science and technology as their careers. Please raise your hands. How many of you want to choose your careers in science and technology? Good. So, Professor Haldane, you have a good audience. Please excite and motivate them. Thank you very much. Now, I request Professor Vijayalakshmi Saxena to introduce Professor Haldane to the august audience present here.
A very good morning to you all present here in this hall. Respected Chancellor of this university, Dr. Mittalji, and Nobel Laureate Mr. Haldane, Dr. Narayan Rao, General President Manoj Chakravarti sitting in front of me, Dr. Rashmi Mittalji, Dr. Ashok Saxena ji, and so many council members are here, ladies and gentlemen, and the media personnel. Really, it is a proud privilege for me to share the dais and to give introduction and to introduce the Nobel Laureate, Professor Duncan Haldane. Dr. Haldane was born in London, Great Britain. After attending St. Paul's School in London, he studied at Cambridge University, where he received a PhD in 1978. His supervisor was the future Nobel laureate, Philip Anderson Duncan. Haldane has worked at Institut Leon Langevin in Grenoble, France, the University of Southern California, Los Angeles, Bell Laboratories, Murray Hill, New Jersey, the University of California, San Diego, and since 1990 at Princeton University, New Jersey, Duncan Haldane is married to Odile Belmont. He received the Nobel Prize in Physics in 2016. About his work, he will tell you all in detail, but just in short while, in 2 lines, I am telling you. Matter occurs in different phases, for example, as a gas, liquid, or solid. At a very low temperature, unusual phases may occur. For example, superconductivity and unusual type of magnetism. To describe these phases and phase transition, Duncan Haldane used 2 concepts of topology, a branch of mathematics. For example, during the 1980s, he explained magnetic properties of chain of atoms in certain materials. In the future, these results may contribute to the development of new material and electronic components. I know you all must be waiting anxiously for the talk by Professor Duncan Haldane. So, without taking much time, I request Professor Haldane to deliver his talk.
Thank you. Have I got a speaker? Oh, here, okay. Thank you. I'm going to tell you about something scary, which is quantum mechanics, which people find some of the most difficult to understand aspects of physics, but I will try and be simple. And what is happening today, there's a huge amount of excitement. There's a kind of new, people are calling it a second revolution in quantum mechanics, because we're starting to see that we have the possibility of building new ways of processing information and manipulating quantum states to possibly create new kinds of computers which will be much more powerful than what we have today. At least that's the dream. And underlying all this is a strange property of quantum mechanics that Einstein couldn't really accept, called entanglement. And I will start to tell you about this. Okay. Is this working? Okay. So the modern laws of quantum mechanics were established in the period 1925 to 32, And listed on the slide are the heroes of this early days of the first revolution of quantum mechanics: Heisenberg, Schrödinger, Pauli, and Dirac. And they discovered the laws of quantum mechanics, and they haven't changed since then. So the basic laws were established in this creative period 25 to 32. And all the tests to date have confirmed quantum mechanics. People have found it very difficult to accept some of the conclusions, but all the experiments that people have done to try and falsify quantum mechanics have failed. Quantum mechanics seems to be the correct description of the world around us, even though we're such large objects compared to atoms that we don't see on an everyday level the obvious effects of quantum mechanics. But anyway, so quantum mechanics is an old subject, but just because we've known the laws for such a long time doesn't mean we actually know everything that they predict and allow to happen. And there's a parallel with electromagnetism, which Maxwell wrote his equations down way back in 1864. He finalized the last equation, the Maxwell term in the Maxwell ampere law, the fourth equation of electromagnetism, and the equations have held firm since then. And there's a story that at the time people asked him, what's it good for? And the Chancellor of the Exchequer, the British finance minister of the time, who later became the Prime Minister, Gladstone, is reported to have asked him, Mr. Maxwell, Dr. Maxwell, this is all very interesting, but what's it good for? And he's supposed to have answered, Sir, I cannot tell you, but I do know one day you will tax it. And of course, electromagnetism has been the foundation of all the technologies which dominated the 20th century. And it's still a new subject. It's still a new subject. In recent years, something called photonic crystals have been discovered, and now a very fruitful subject of research. So electromagnetism, of course, led to lasers, and it's still, even though the equations have been static since 1864, it's still yielding new technologies. So starting around 1980, there were new insights into quantum mechanics started to emerge, and new unexpected states of matter, which are now people call topological states of matter, quantum states of matter, were discovered. And these kind of unexpected new states have got married together with new ideas from quantum information theory, which was a subject that Richard Feynman initiated in the late 50s when he started thinking about what kind of engineering could be done on the atomic scale, where quantum mechanics plays an absolutely fundamental role. And he gave a very famous public lecture, which was called There's Plenty of Room at the Bottom, which is referring to the very small scale of atomic scale of matter. And I think that was an allusion to a controversial play at the time called Room at the Top. But anyway, this ideas of quantum information theory started maturing in the late 80s and 1990s, and they've come together and really got married together with some of these new discoveries of new kinds of states of matter to make people start to believe that the dream of the quantum computer may someday come true. And so, as I say, people are now thinking that this may be the second quantum revolution, a kind of a new way of changing our thinking about quantum mechanics, where we, instead of just looking at states, looking at matter and hitting it with a hammer, basically smashing a quantum state, we start to gently poke the quantum states around and manipulate them in a very delicate way to enable us to do things like process information in very novel and fruitful ways. Okay. And I think in the next 10 to 20 years, we're going to see some of this technology come to fruition. But, you know, things take time. One point one can make is nuclear fusion technology has been an obvious candidate for solving our energy problems, and it's still taking longer than expected to come to fruition. So one can't really make promises in this matter. Okay. So anyway, the key message is that as we understand the quantum mechanics better with new ways of thinking about it, new and strange possibilities are emerging for the materials of the future and the technologies that they will allow. Okay. And, okay, so what is quantum information? Classical information in the computer is stored in a bit. Basically, it's a switch which can either be on or off. It's a number 1 or 0, which make the binary numbers. And so a switch is a classical object because you can think of it as, on an atomic scale, of lots of little atomic magnets all pointing one way, and you throw the switch and they reverse to all point the other way. But quantum information is not stored in this on-off way, which is just a two-state system. It's a quantum two-state system, but a quantum two-state system it can be represented not just by an up or down, or two numbers, 0 and 1, but actually a direction that points on the direction of a sphere called the Bloch sphere. So there's a lot, when you look at the quantum states of a single spin, the most elementary quantum mechanical object, then it's got a much richer representation in terms of basically a full three-dimensional direction. So there's clearly a lot more information that can be contained in it, but it's much more subtle to process it. So any system with two states, two quantum mechanical states, is equivalent to an electron spin. Okay? And now it's called a qubit. Okay? So anyway, so the interesting thing about the quantum mechanics is this very strange property called entanglement. And this is actually now, this used to be a philosophical issue, an objection to quantum mechanics that Einstein raised in the 30s. But now entanglement in recent years, because of this fusion between quantum information theory and actual experimental results on strange states of matter, it's now become a practical rather than a philosophical issue, and in fact, it's viewed as the fuel. Entanglement is viewed as the fuel which would drive some possible future quantum technology of quantum information processors. Okay, so what is entanglement? So despite making this really early contributions to quantum mechanics, and you may not know that the subject that Einstein got his Nobel Prize for was not his remarkable theories of special or general relativity. It was actually his citation was for early contributions to quantum mechanics, something called the Photoelectric Effect, which describes when light shines on a metal whether or not electrons get emitted, and this thing is used these days to stop garage doors with an invisible beam. If you walk through it, it stops the garage door from coming down and chopping your head off. So it's a very practical thing, the photoelectric effect. And this is what he got his Nobel Prize for. So he was one of the early innovators in quantum mechanics after Planck. But by the 1930s, he'd come around to reject the quantum theory because it seemed incompatible with his notions of relativity. So he identified this key property that quantum mechanics predicts called entanglement, and which he calls spooky action at a distance, and the more polite word for it was coined by Schrödinger. And he felt this was so crazy that it had to be wrong, that quantum mechanics had to be wrong, and if experiments were ever done to check this, they would surely discredit quantum mechanics and show it was only an approximation to a more fundamental theory, which he hoped would have something called local realism. Okay. But one of the fundamental properties of quantum mechanics is the Pauli exclusion principle, due to one of these four people I showed at the beginning, Wolfgang Pauli. And the Pauli principle says that two electrons, which are particles called fermions, can't be in the same state. And there are actually two kinds of particles classified by their properties under exchange, if you swap two around. And the other particle type, which was referred to in the introduction, of course, has got a deeply Indian background. The boson is named after J.V. Bose, who pointed out the possibility of what's now called Bose condensation in the 30s as one of the early developments in quantum mechanics. So fermions go back to Fermi, so I'm actually concerned with fermions in this talk. But two fermions or two electrons can't be in the same state. But in fact, the matter that we're made of we're made out of molecules which are held together by the chemical bonds, the basic thing, the basic structural property of the matter around us. And the chemical bond is basically made by joining two atoms together and linking them in a fixed geometry by putting two electrons in between the two, so the negative charge of the electrons stops the positive charges of the atoms or ions from repelling each other. So superficially, putting two electrons in the same place is a violation of the Pauli principle, which says you can't do that. But the way the escape from that is that the electron is more than just a little charged particle. It's a little spinning charged particle. It's spinning like a little top, like a child's toy. And the electron, the quantum mechanical properties of the spin are such that it's a two-state system. There are two possible states of the spin relative to any particular axis. They can point up or down. And so the Pauli principle says you can't put two electrons in the same state. Well, being in the same place is not all there is to an electron. Because they also have this spin, I can put two electrons in the same place, basically provided they have their spins exactly pointing in the opposite direction. Because if the spins are not exactly anti-parallel to each other, there's some component, when you resolve this, you swap the two around, you pick up a minus sign, which you see in this, let's see if I can use this pointer here. No, it's not, I didn't start it, okay. But they can be pointing in opposite directions, but they don't have to be up and down. They can be pointing back and front. And the thing is, the state of the electron is 50% up down and 50% down up, or vice versa. So, and this is actually the poster child for the entangled state. The maximally entangled state of the two electrons is in the state where if one is up, the other one's down, and if the first one's down, the other one's up. And this is one of the weird things of quantum mechanics, that the electron has to be, each electron doesn't have a definite direction of its spin. It can be either one or the other, but the other one has to be the opposite one. And Einstein was greatly worried about the thought experiment, because he loved thought experiments, of if I stretch this chemical bond to a large distance, and I did a measurement, and you don't know which direction the electron's in. All you know is that the spin of this electron is opposite to the spin of the other one. But if you measure the direction of the spin, you immediately know where this one's up. It immediately applies that if anyone instantaneously does a measurement on the other one, it'll always be down. And vice versa. If it was up here, down here, it would be up here. And Einstein felt this meant this was a violation of relativity, because he thought it was something like sending information instantaneously over large distances, right? And in fact, it's not a violation of relativity, but he came up with this thought experiment to try to measure what happened if you could stretch something like a chemical bond to large distances, and this is called the Einstein-Podolsky-Rosen Paradox. And in fact, in 1935, one of his colleagues, who I believe he got very angry with, Rosen, he went to the New York Times, and the New York Times published a front-page story that Einstein contradicts quantum mechanics. And probably there wasn't much other news on the day that such a physics topic had happened. There were no invasions of countries happening then. But in any case, Einstein was actually quite angry about Rosen going to the press, because he felt that scientists shouldn't wash their dirty linen in public. They should keep their little problems inside the community. But anyway, this got publicized, and it was the Einstein-Podolsky-Rosen paradox, which kind of was a challenge to quantum mechanics. Well, as I said, Einstein thought that when this measurement was actually done, it would discredit quantum mechanics. And it took a long time for the measurement to be actually done. And other people analyzed the Einstein-Podolsky-Rosen paradox more carefully. And in particular, first David Bohm, and in particular then John Bell, formulated it in a very clear fashion and introduced what are now called the Bell's inequalities, which a local realism theory, a classical theory of the kind that Einstein wanted, could be ruled out if you did some measurement, and the measurement results, I think, were above some threshold. So his measurements were not so much to measure up and down, but measure two different axes in all different directions and come up with a much stronger thing. And in fact, the experiments were done in the 80s by, I believe, possibly firstly by Alain Aspect in France. At least that's where most of the publicity came from. And the experiment, of course, showed that quantum mechanics was 100% correct. Otherwise, I wouldn't be talking to you about this here. But of course, so in principle, you can stretch something like the chemical bond and keep it in this quantum entangled state, but it's very fragile against interaction with the environment. And this is the big problem of trying to use this entanglement in a quantum computer, that the entangled states, the electron tends to, or the couple to something else locally, and then the information in it gets lost and dissipated in the environment, and this is the big technical problem of trying to use this. Well, Aspect's experiments were actually not done with electrons in a chemical bond. They were done with a different system, a boson system, in fact, of photons, light, and just as the electron has spin that's up and down, the photon has two states of polarization, which is what your sunglasses are trying to shield you from when polarized light, which is polarized horizontally, gets reflected from the road. So the kind that's best for the spins is actually circular polarization, which is the light can either be left-handed or right-handed as it goes towards you. And but optical fibers are now they allow you to propagate things over large distances under the ocean, and you can maintain entanglement of photons over intercontinental distances. And in fact, as we can see, some of the new developments that India's neighbor, China, has been putting a lot of money into in this thing has actually led to demonstrating entanglement between photons linked by a satellite link. So even much larger than geostationary satellites rather than oceans. So this principle of entanglement at least can be, at least for photons, has been maintained, and there's a lot of interest in quantum communications based on this. Oops. So around 1980, the condensed matter theorists, of which I'm one, and actually India has a large history of people working in condensed matter physics, they thought they had a basic understanding of electronic and magnetic properties of materials. And, one can't be complacent in science, right? Science is full of times when people think they've understood everything and there's nothing more to be done in the subject. And then, of course, something turns up to show they were completely wrong about a lot of things they thought about. So, around 1980, there were two examples of weird properties showed up, which didn't seem to be understandable in terms of the basic understanding people thought they'd achieved by 1980. And now we know these are examples of this new kind of topological quantum matter, which turn out to be condensed matter, which means solids and liquids, basically, where the atoms are kind of in close contact. It turns out to be states of matter where the quantum entanglement plays a crucial role. And the previous normal kinds of matter that people thought they had a good understanding of, really, the entanglement properties were not playing an important role at all. And no one really thought about entanglement as a property in condensed matter. They'd always thought of entanglement as some kind of philosophical objection to quantum mechanics that theorists worried about. But so it's not surprising that these materials were difficult to understand at first, because they were the first materials in which this entanglement property was really playing an absolutely crucial role. And these two things, my contribution at the time was on something rather obscure and very academic, models of magnetic chains of atoms, which was a very theoretical thing at the time, although now we can actually make little magnetic chains by moving things around on the surface of moving little magnetic atoms around on the surface of a crystal with an atomic force microscope. So again, we see that in the intervening period between 1980 and today, we've started to achieve a large amount of technological ability to actually move and play with atoms and put them in places and do interesting things with them. And the other amazing discovery at that time was the quantum Hall effect, and both of these two discoveries were completely unexpected, right? The quantum Hall effect was an experimental discovery, and mine was a theorist discovery. So the experiments were immediately there and were very convincing. It took some time for the experiments to kind of prove the theory that I did was correct. But these two things had no obvious connection to each other at the time either. But they turn out to be both linked by this relationship to entanglement. And in the meantime, many, many more kinds of topological quantum matter have been discovered, especially in the last decade, where new extensions of this idea led to people realizing that there was topological matter around sitting on laboratory shelves that no one had noticed had this property, and because no one had known where to look to see it. And so the metaphor here is the iceberg, the peak is showing above the surface of the sea in 1980, but leaving this huge amount of extra stuff below waiting to be found. Okay. So as I say, the unexpected properties really of topological quantum matter caused so much excitement in the last 10 years, and that's really what led to this 2016 Nobel Prize, even though some of the early work was done much earlier than that. Right? And part of the excitement is because they seem to offer a plausible way to overcome the difficulty of protecting entanglement in topological quantum computers, to avoid the loss of information by degrading it and losing it to the environment, which is the main stumbling block to turning the theoretical proposal of quantum computers into a reality. So what is topological matter? It's actually quite simple in some sense. Topological matter differs from ordinary matter because it's got properties, entanglement properties that can be described by simple whole numbers, integers like -1 or 2 or -5 or 4. So the thing is that states of matter which are described by like integers, whole numbers, they can't smoothly change into each other. So there's always something interesting happening at the boundary between one type of quantum matter, one type of topological matter and another. So if I have this on the screen, you see this type of matter which has been classified with a region classified with the number -2 swimming in the background of a boring region classified by a number like 0, although 0 is not really a boring number, but you can see that you can't change continuously from -2 to 0, so there has to be a boundary at where this changes. And in fact, some of the early properties of quantum matter were hidden on the boundary, on the surfaces of crystals which had this property, and no one had actually seen it because no one had known about quantum topological matter, so no one had gone looking for it, and it sat under people's noses for many years. So why is that? Another point that comes about from this is that topological properties of matter can't change continuously, which actually means that if this property is important for something, it's robust against the small amounts of dirt on the sample. And this is quite a contrast to all our current day electronics, which is based on silicon technology, where you have to make these ultra clean silicon wafers in a clean room where everyone is protected, where everyone is wearing white suits to protect the silicon disk from getting a little speck of hair or a flake of sweat or something onto it, which would ruin the disk. So the ultra-clean systems, ultra-clean rooms are needed for current-day technology, but the topological stuff is kind of forgiving in the sense a little bit of dirt will not alter it. It has to be a significant amount of dirt. And what's the classical example? Topology is a mathematical word. Okay, it's a property of mathematics. It's not a physics word. And the classic example in mathematics is the classification of closed surfaces by what's called the genus, which is just counting the number of holes through the surface. And in fact, the Nobel committee, when they were introducing the prize, they went through a lot of contortions to use the metaphor of donuts and coffee cups to try and explain topological matter to the press who were waiting to ask what's it good for, right? So a shape like a sphere with 0 holes, like a rugby ball or a soccer ball, you can easily push on a rugby ball or a soccer ball to kind of distort it. If you squish it enough, you can change its shape a little bit, but those have the same topology. The thing which has a different topology is the donut or the bagel, where there's a hole through it. So to change a soccer ball into a rugby ball, you can just squish it a little bit, but to actually change it into a donut, you actually have to do a lot of violence to actually make a hole through it and do it. So you can see the hole is a topological thing. There's no such thing as 0.3 of a hole. Holes come, there's either 1 hole or 2 holes or no holes. And actually, this was the great discovery of Carl Friedrich Gauss, the great German mathematician of the late, the early 19th century. He felt his most important mathematical discovery was actually this remarkable theorem from topology, which is actually something almost a high school person could understand. In high school, you've learned that the surface area of a sphere is 4 pi r squared. At least that's one of the formulas that the school students have to kind of memorize to pass their math exams. And the curvature of the sphere is constant at all places, and the curvature is the product of 2 independent radii of curvature, each of which is 1 over r. So for a perfect round ball, the radius of the Gaussian curvature of the sphere is 1 over r squared. So Gauss discovered the rule that if you integrate the Gaussian curvature over the surface of a sphere, 4 pi r squared times 1 over r squared is just 4 pi. And that sounds like a very trivial statement, but what he discovered was that if I bend the sphere into a rugby ball or bend it into a banana or some other shape without making any holes in it, the answer was still 4 pi for the integral of the Gaussian curvature over the surface, although it's a much, much more difficult calculus calculation to do. And he actually he gave this a Latin name. He called this his theorema egregium, his most unexpected result of his life, that the answer for the integral of the curvature over the sphere was still 4 pi when you deformed the sphere. And if you put 1 hole in it to make it a bagel, which is the analog of the coffee cup, it's got 1 hole and the 4 pi goes down to 0. The formula is 4 pi times 1 minus the number of holes. So each time I add a new hole, the integral goes down to minus 4 pi, 8 pi. So this is the first object here is the movie that all the experimentalists working on anything to do with topological matter show is a movie they pick up on YouTube where a coffee cup changes continuously into a donut and backwards. But then you can have this one here, with 2 handles. This thing is called a loving cup. It's got 2 handles. It's got genus 2, and so we do the integral over it. It's minus 2. The bits of negative curvature are the little bits on the inside of the holes. And actually, the third one is, I actually have an example of it. I didn't bring it. I forgot to bring it with me. The 3-handle object. And again, I'm not sure what this is called. Some people suggested it's called a California loving cup, but I'm not sure about that. But anyway, it's got 3 handles and 3 holes. And it's a minus 8 pi. So what Gauss discovered then was this remarkable connection between topology and geometry. Curvature is geometry, and counting the holes is topology. And he found that you could relate the 2 things, and that was the foundation of the whole mathematical subject of topology. Well, mathematicians like to make things. Gauss was thinking about physical surfaces, physical 2-dimensional surfaces like surfaces of balls, but mathematicians like to make things much more abstract, and in fact, in 1944, the Chinese mathematician Chen, who was working in America at the time, he kind of made a much more abstract version of the Gauss theorem, so it's now called the Gauss-Bonnet-Chern formula. And he turned this thing into the formula which is actually used in this quantum mechanical aspect. So the quantum mechanics have got nothing to do with coffee cups and donuts, but it's the same mathematical principle that Chern managed to make it in a much more abstract way. And in fact, one of the mathematicians don't have a Nobel Prize, but one of the medals that you get the Fields Medal is the most famous one, which is restricted to young mathematicians who are under 40, under the idea that no mathematician has got anything important left to say after they're 40. Hopefully, physicists are not treated in the same way by this ageism. But anyway, the Chern medal has the formula on the back. It's the same Gauss-Bonnet formula. Okay, so in 1981, I discovered what's called a spin-1 magnetic chain, where the magnets really are like two of these elementary quantum spins, which are spin a half, but glued together to point in the same direction, had this novel state that's really understood as the simplest of the topological states. And the previous ideas about magnetism thought, well, the atoms had their little magnet moments, which are represented by the spins, and at low temperatures they can point in various ways. The ferromagnet, where they all point the same way, and which you can use to pick up a paper clip, is the most common one that you know about. But there's others, antiferromagnets, where one points up, the next one points down, the next one points up, which is shown in this picture here. And it turned out that the state I found had finally after more work and other people's interpretations of it, it has a very simple picture in terms of entanglement, where you can see the two neighboring atoms, the two spins kind of divide in two on each atom and join hands. One goes to the neighbor and one goes to the left and one goes to the right. And if everything joins hands, you can see there's always one left over at the end. And this is if you try to cut this in half, you see there's a barrier, there's a kind of entanglement between two neighbors, while the regular magnet, you could just sort of assemble, bring magnetic atoms together and just put them next to each other, up, down, and there's no entanglement. So this was had unusual properties, and basically no one had thought about a state like this at the time, which was why it caused so much controversy. But actually, in science, arguments between theorists are finally settled by experiment, at least in condensed matter, and perhaps in string theory, where it's very difficult to have experiments. I don't know, but in condensed matter, in the end of the day, some very clever people who can know how to make materials will now make a material that satisfies the toy model that was used to find something interesting about it. So the chain of magnetic atoms was actually made by some nickel atoms in some organic compound called NEMP. And in fact, the experiments in the end proved the ideas I'd introduced correct, which at the time some quite senior people in the field had denounced as complete nonsense because it didn't agree with the earlier ideas. And of course, nothing is better for the career of a young person to actually get people attacking him and then him being proved right. Of course, experimentalists love to get involved in these controversies. The favorite thing for them would be to prove somebody wrong, but the second best, they also like, if they can't prove somebody wrong, they like to prove somebody right. And anyway, this was good. So actually, controversy and struggle for new ideas in science is always good. And in fact, the attempt so many people got interested in this controversy, and they devised all kinds of new experimental and theoretical techniques to look at it. They've actually, all the new techniques they devised have been extremely useful for other things in the future. So controversy and struggle is actually what leads to new things emerging. And anyway, it was a very interesting period. So again, the metaphor for this thing is really people holding hands. You know, most people have two arms, unless they've had an accident or something. And you'd say, well, how can you have a one without accidents? How can you have a one-handed person? Or how can you have a free arm by itself? But if a chain of people hold hands, you can see the hands where they're holding are all fixed, but there's a free arm which can can do what it wants at either end of this chain. And this is the typical example of a topological matter where there's something at the boundary between normal and topological. In this case, it's a free, the thing was made out of spin 1 objects, but there's a free spin half at the end. Anyway, this turned out to be something like the simplest example of topological matter, which is, why it's become so famous. And it was at the time unexpected, and the theme of, in fact, all the 3 Nobel Prize winners of the year I got it have this theme of doors opening to a hidden world. And the picture of the chain, the spin chain, is as a kind of snake, is showing in my certificate with a kind of the entanglement up down minus down up. The thing here. So the quantum Hall fluids, actually, the other state was some of the most clearest examples of topological states. They originally found, this is a property of electrons in very strong magnetic fields, and in magnetic fields, electrons want to go around in little circles, and if they're moving in empty space, they go around in a spiral, but if they're stuck to a two-dimensional surface, they go around in a little circle on the surface. And one of the most amazing discoveries that got a Nobel Prize pretty quickly for Klaus Klitzing was that when he did some measurement of something called the Hall conductance, electrical measurement on these systems of electrons bound to a two-dimensional surface, which was made in a silicon device in a strong magnetic field. Then he measured things and he got the electrical conductivity or the Hall conductivity to be a whole number, an integer, 1, 2, or 3, etc., times fundamental units involving the electron charge and Planck's constant, the fundamental property of quantum mechanics, without any reference to the details of the material. And this was like totally unexpected. Everything should depend on how clean or how dirty the material is. And here you're getting this perfect numbers coming out. And in fact, this has been technologically very important, at least now, because a few months ago, the kilogram, which used to be defined by a lump of platinum kept locked in an office in Paris, has now been replaced by a machine based on something called the Kibble balance, which is based on this remarkable topological property of the Hall conductance. Okay. So the topological nature of the quantum Hall effect took quite a long time to become clear. Little electrons go around in little orbits, but the system actually has to have a boundary. The electrons have to be confined in some kind of sheet, and they go around in a little box. And when they hit the ones that hit the boundary don't make a full circle. They kind of bounce around and they go around in the opposite direction. If you think about it, they're going clockwise in the bulk, then they'll go anti-clockwise. The ones that hit the wall go in a kind of skipping thing. And so actually this thing which goes round in one way around the wall of the system in the opposite direction to the rotations in the middle is in the edge state, a typical topological feature. And in fact, the way it works is that the energies of the electron orbits in the middle are all the same, but they get altered. The ones that hit the wall have a different energy, and you get this picture where there's a so-called quantum energy gap in the bulk, but the quantum state, something called the Fermi level, the highest occupied electron state, is pinned at the edge, and you can move the edge properties up and down a bit without affecting the fact you have this energy gap in the bulk. So again, you don't need to fine-tune the magnetic field to see this, and this is how von Klitzing discovered his effect. He put his sample inside with a constant current flowing through it. He put it inside a big magnet, switched the magnet on, and every time he switched the magnet on, the conductivity measurement, the voltmeter was showing exactly the same number on a digital voltmeter every time he did the experiment. So first he thought his digital voltmeter was broken in some way, because how could you get the same number to 4 or 5 significant figures coming out each time you did the experiment? And if he'd done the experiment a different way, by putting it in a fixed magnetic field and switching on the current, he'd have never got the same number each time. So he had the luck to do the experiment the right way, where it became immediately obvious to him that something amazing was going on, while earlier people had done similar experiments the other way and never noticed anything. So again, if you don't know something's out there, no one else is looking for it, and you might be the lucky person who stumbles over it. So there's a huge amount of luck involved in finding these amazing discoveries. So I guess, so the topological stuff was not recognized initially, and in fact my co-laureate David Thowless was one of this group of people who came up with a formula which was a whole number formula for this Hall conductance. And they just came up with this formula and said, well, we found out why it's an integer. And then some mathematical physicist, Barry Simon, made a connection between work that Michael Berry, now Sir Michael Berry, had done on essentially curvature, on the geometry aspect of quantum mechanics. And they realized that this formula was just this Gauss-Bonnet-Chern formula that the mathematician Chern had discovered in 1943, without any idea that it had any relevance to anything real in the world. It was just pure mathematics. And so this turned out to be very seminal, and this whole Berry phase and the curvatures and formulas are kind of key idea in understanding the new kind of new things in quantum mechanics. And I feel that Michael Berry should get a Nobel Prize, but we'll find out if he actually gets it. So anyway, so my contribution to this was also that people needed very high magnetic fields to create this quantum Hall effect thing, to make the electrons go around in little circles. And then I realized somehow that the basic principle didn't involve high magnetic fields, it involved breaking so-called time reversal invariance. That means if I took a movie of something and I showed it backwards, it would look different. So if things only go one way around the boundary, that's broken time reversal invariance, because if I showed the movie backwards, it would be going in the other way, right? You can tell the difference between showing the movie forwards and backwards. And so in fact, just magnetism is able to do that, and this was the toy model. Again, a very simple theorist toy model that I came up with in 1988 as just part of an argument about whether you needed magnetic fields or time reversal invariance was all you needed, etc. And this turned out to be a toy model, but it was incredibly influential because it actually has led to the discovery of the topological insulators, which was this big thing. And so my model was sort of there sitting around for many years as a theorist's kind of curiosity, very useful for various toy calculations. But these chaps, Charlie Kane and Eugene Milly, they kind of just took a very simple generalization of my model and found that it had obeyed a topological principle which was more general than the Chern formula, and it led to some of the discovery of three-dimensional crystals which have this strange properties. And in fact, again, showing about how much money is being put into condensed matter experiments and really revamping their universities in China, the people who eventually did the first physical realization of my toy model and turned it into reality were people in Beijing. And so now it's become quite an interesting thing because you can do lots of interesting things with it. So without magnetic, so the interesting thing is that you've got stuff that goes one way around the boundary. So you can have something like a divided highway. So if you look outside here and take the road from Delhi to Jalandhar at night, you'll see it's pretty good. There's a wall down the middle to keep the trucks on one side not interacting with the trucks on the other side. Well, electrons in a regular wire, they kind of, some are going one way and some are going the other way. Quantum mechanics helps to sort them out. But you can see that actually if you could separate the stuff that moves one way from the stuff that moves in the other direction, have a divided highway, it seems to have some possibility for much cleaner information transport. And so there's a lot of possibilities in now we've actually physically realized these kind of one-way edges and things. And in fact, you can do the same principle turned out to be applicable to light, that you can also, by basically doing something which is analogous to magnetism in light, that break time reversal symmetry in some photonic crystals, you can make light travel you can make systems which can only allow light to travel in one direction. So if you put a boundary, a wall, to block it moving around, since the light can't reflect backwards along the edge it came from, it just has to go around the boundary and snake around it and go along. And so there's a lot of these kind of very unexpected sort of things that people started finding. And in fact, even more unexpected things followed. Something called more Nobel Prizes came out of this stuff. The fractional quantum Hall effect, in some sense, is a version of von Klissing's result, which is even much more extraordinary because it involves fractional charges and fractional statistics, which are not bosons or fermions. And that, in fact, you can see the nice thing about topological states is that the device in which this was discovered, it looks like the person who made this device would certainly not get a job at Intel, I can tell you that, right? It's got but the forgiving nature of topology allowed this remarkable effect to be demonstrated in this device, which was made at Bell Labs by Art Gossard here. So where does the quantum computing come in? I'm wrapping up to finishing. The Lofton state and these other states, the so-called abelian states of quantum Hall state, they have very interesting properties, fractionally charged excitations, but even more remarkable ones are something called non-abelian ones. And these are the things which, in principle, could support universal quantum computing. And this is what people are struggling to actually turn from a theorist's idea to a physical idea right at the moment. So in this thing, somehow you've got a picture of some kind of defects, which you braid them around each other and you kind of process information. And this is actually the route to quantum computing that the Microsoft have put about $1 billion into. I mean, there's lots of different proposals for quantum computing. There's lots of competing ideas, so it's a kind of rich field. But this idea is simple. You have this quantum state. You've got these edge states that move around the system in one direction, but I can have little vortices in this fluid, which also have little edges around them. And the remarkable thing in the non-abelian state is that there's one piece of information for every 2 vortices in the system. So, and you can process information by moving them around. And how can that be? Well, first of all, the quantum computer in some sense tests all solutions to the problem at the same time, which is why it's a remarkable idea. And where the information is, if you create this vortices, the information is stored in the system by how you create it. So the information could either be between the top pair of vortices and the bottom pair of vortices in this picture, or vertically between the others. And if I move one around the other and stir them, it kind of corresponds to changing a state of the qubit. So the information is not locally stored. It's somehow spread out through the system, which is what makes it safe against interaction with the environment in principle. So the information is somehow, once the vortices are far apart from each other, the information is spread out, and this is really the key thing. To get the information back again after processing it by moving these vortices around it themselves, you have to bring them together, and then it's more dangerous to lose it. But anyway, that's the sort of basic idea, and in fact, there's some calculations that if you look at where the vortices are, which are these kind of yellow blobs on this picture, the pictures look the same. If you look very closely and they're reasonably close together, you see a very, very fine pattern of little waves in the system, and the shape of the pattern distinguishes the information. So the 2 states here, which you probably can't see, the one on the left is, say, the up spin, the other one would be the down state of the qubit. And if you make a state pointing sideways, the pattern would be a mixture of the 2. But once these things move far apart, you can't really detect the pattern anymore, and the information is safe. And this is the idea, the beautiful dream of scalable, topologically protected, scalable quantum computing. So as I say, it's taken a long time to get fusion power, even though the theoretical idea of fusion power is very compelling. All we have to do is, is fuse the atoms of lithium together and we'll get a huge amount of energy out. But the difficulty is holding them together long enough. Same thing, technical people and people investing money, of course, have to be a bit skeptical about the beautiful ideas of scientists, but I personally think there's so much work going on in this subject, and things are getting better so much quicker than people expected. I mean, I used to be very skeptical. Nah, we'll never have this. But actually, progress seems to be surprisingly fast because so many different people are working on this from different viewpoints and different ideas, and then it's advancing everything. So the Microsoft idea, let me just finish on this, is actually the braiding of so-called Majorana zero modes, which were the things I was trying to show in those pictures, the little vortices. They've moved over to a version of this based on a so-called 1D topological superconductor, which is a device made with indium arsenide nanowires on a superconducting aluminum. And they haven't achieved braiding yet, but it's actually a very simple toy model behind this due to Alexei Kitaev, one of the people I showed in the picture a few slides ago. And again, you put this nanowire, which is like a chain of little atoms. They form a little crystal. It's actually you put this nanowire together with a superconductor. Kitaev's toy model is like a chain of atoms. And they interact with a superconductor. And the thing is that when you interact an electronic orbital with a superconductor, you lose the electron state becomes kind of, you can divide it in two in some way. It's a bit like dividing the spin 1 into 2 spin halves. So when you put the electron chain in contact with a superconductor, it splits each electron state into something called 2 Majorana states, which is what all the kind of excitement and fuss about recent years has been. And essentially, you do something with a magnetic field or whatever that makes them kind of split up and join up. They split up and then join together with their neighbors. And again, you get this same principle that now, instead of being separate, they're entangled with each other by this joining up thing. And then there's something like the 2 free hands left at the end of the chain. And those 2 free objects are these Majorana zero modes that you kind of braid around and stuff. And as I say, this is just one of the... So toy models play a huge role in actually helping people to think creatively about how you would do things, and then of course you need to proceed from toy models to how would you actually realize this in practice. So what I described was actually the Microsoft approach, which is one of the current ones, but all the other big players in this field, like Google, are big in this thing, and the Chinese government is big in this thing, and because of that, we're getting the US government, seeing the Chinese government doing all this stuff, has now announced a quantum initiative. So maybe Mr. Modi should be convinced to have a quantum initiative here. Anyway, so finally, the moral of all this is that 3 communities of people come together, mathematicians, toy model builders, material science things, and a whole lot of fruitful things emerges from that. So finally, my motivational message to student audiences, why I'm here probably is that I had good mentorship, which I guess was also mentioned yesterday. A mentor is an incredible thing. My mentor was Philip Anderson, who also had mentored a number of Indians. And he helped me to think outside the box a little bit when presented with a new problem. But the basic thing, you have to have luck to come across these new things. You can be an incredibly brilliant, Einstein-like genius, and most of the time, Einstein, of course, is a special case, but doesn't mean you're going to be lucky enough to discover something that no one was expecting to find, including you, right? You can do incredibly good work. So I think anyone who goes into basic research has the possibility of getting a Nobel Prize because as long as you're doing something which hasn't been done before, there's a chance that you see something that really wasn't expected. Now, of course, you need a preparation to exploit your luck in this thing. So you do need the luck to kind of come across something which wasn't expected. You do need the preparation to actually realize you found something interesting. And actually, you probably need a lot of commitment because anything new, if it's not obvious, actually kind of often has resistance against it, and you need to fight for your ideas. And of course, actually, luck, preparation, and commitment are the standard thing for business too. But for success in most realms of life, you need to have some passion to drive you and things. So anyway, so that's my message is anyone doing basic research and you take the time to explore something unexpected, you find most of the time you'll find a very simple explanation or no explanation at all for the unexpected thing, but very few times some kind of diamond will emerge as you kick the sand in the road, and if you're not looking at what you're kicking, you'll miss the fact you unearthed a huge diamond and just walk on by. But anyway, so finally, as scientists, we need to make an effort to kind of outreach to the public and get people to excite politicians and people to actually fund science. And here's my attempt to explain Chern-Simons theory and topological stuff to a prominent political person or non-political person. Thank you.
To take some queries. Sure. Okay.
Our Nobel Laureate has kindly agreed to take few of the queries and questions from the students or delegates, if any.
Yes, please. Please identify yourself and give the comment on the question.
I'm P.K. Sinha. I'd like to pose a particular question about, I'm not sure whether that word is quite, seems to be dabbling in a way in some kind of adjacentness. But what is that, can there be some basis for turbulence and the chaotic emotions or chaotic behavior in the kind of adjacentness, which might be a very kind of entanglement we're talking about?
Well, entanglement is a very specific quantum mechanical property. Two things are entangled. If they're unentangled, if they're not entangled, you can measure a property of one thing and it doesn't affect the measurement of the other thing. You know that if it's, from one of the basic things in quantum mechanics, if I do a measurement, if I measure the position of a particle, I lose information about its velocity and things. So if I measure things, I actually do something which the so-called Copenhagen interpretation has language like you collapse the quantum state. I don't worry too much myself about measurement. I view myself as a kind of quantum mechanic, and I'm trying to understand. I'll take the laws of quantum mechanics as given and see what they do. But so if you measure something on one particle, you rule out the possibility of doing a simultaneous measurement of something else on it. So if they're entangled, if they're not entangled, you can measure what you want on this particle over here, and it doesn't have any effect on the quantum state of the particle. On the other hand, if they're entangled, if they're completely entangled, you measure something here, you completely fix what a measurement in the other particle would do. So if you measure this one to be up, the other one is down. If there's some partial entanglement, which happens, then you lose some information. So the entanglement is really something to do with about information that's stored in quantum states. But yeah, I didn't really fully understand the full aspect of your question, but it's a...
What I'm saying, is there a possibility of a coupling between the two measurements, assuming the existence to occur, assuming the existence of the two levels of measurement?
Yeah.
Can there be coupling, and what sort of coupling?
No, yeah, it's not really, so Einstein worried about the thing as information traveling or something. The current kind of picture is something called consistent history. So there's no real coupling between the measurement, what you're doing in the measurement, you're restricting the possible quantum states of the system, and if the thing is in this entangled singlet state, there are no states where both of the particles are up or down. They're only up, down, and down, up. And when you do a measurement, you're not really, the entanglement isn't thought of as a physical connection, but it's some kind of information restriction between the two things, yeah. Uh-huh.
I want to know your views about quantum consciousness.
Ah.
I want to know a bit about quantum theory and consciousness at quantum level. How to
Consciousness is, of course, consciousness is perhaps one of the big issues of the next century, to try and understand anything more about consciousness. I mean, people have. There's no real, no kind of mainstream ideas about quantum mechanics and consciousness, although obviously there's quite a lot of non-mainstream ideas that people float around, but we don't really have any concrete understanding of consciousness. Some people, there have been some ideas that information in the my colleague Matthew Fisher has pushed some ideas that there may be information stored in quantum states in certain kind of ionic complexes and spin-orbit coupling, but we have no idea yet. It's all kinds of strange ideas and speculative ideas have been made, but nothing has really come to any fruition so far.
What is the difference between old kilogram weight and new kilogram weight?
Okay, well, the new kilogram weight is democratic, and the old kilogram weight required was autocratic, because when Napoleon created the kilogram system, right? And so there's a kilogram that was sitting in the Bureau of Measurements in Paris, and if you belong to the metric system, all you could do to check your weight was to basically, effectively go to Paris and compare the weight which someone is using to sell the goods in the shop to the kilogram. Of course, they do it by a series of intermediate things. But now the kilogram is defined by this so-called, but basically before with the kilogram was a lump of metal in Paris, and the value of Planck's constant depended on the value of the lump of metal in Paris. What we've now done is fix the values of the fundamental constants like Planck's constant to make them exact numbers. They're now a decimal number, but it's not an infinite decimal number. It's a number with about 10 places in it, and it's exact.
Thank you, Professor Haldane. Thank you so much.
Yeah.
Thank you. We'll take you can take up the discussions a little later, because
I request you kindly listen to my question in very simple words. And the question was this: you gave an analogy.
Yeah.
आपने हमें एक इस प्रकार की एनालॉजी दी जिसमें आपने कहा, I will translate it for you in English also, and it is a question, it is not a comment, it is a great respect to you. आपने हमें ये कहा कि एक फिल्म चल रही है और उसको हम आगे ले जाते हैं और फिर वापस लाते हैं, उन दोनों में जो अंतर होता है उसके द्वारा आपने क्वांटम हॉल इफेक्ट को एक्सप्लेन किया, और उससे नए नए प्रकार के कंप्यूटर्स बन सकते हैं। ये सब चीज़ें आपने कही। I am asking this thing that a film is going in the forward direction and you are bringing it back, and with that concept you are developing the idea of new quantum revolution. And this quantum revolution, how it is possible, how quantum computers can be framed, do you have any idea, or some persons have already done it? Actually, I am not worried, I am not knowing about it.
Yeah.
It is possible that you may be knowing it because your work has been honored with such a big prize.
Professor Saab, मैं आपसे गुजारिश करूँगा.
I will request that please explain this thing to the public.
Okay,
Professor, let me, Professor Haldane.
So the quantum computer does not yet exist, and many people are trying to find a way to make it. What the ideas or the results that were honored were because one of the fruitful we've learned a lot of new things about quantum mechanics in this last 40-year period, and some of these things have led to this new ideas of new materials and new ideas of quantum information. In theory, these things could give us so-called topologically protected quantum information processing computers. The big difficulty with the quantum computer is that the quantum computer would be an amazing thing because in some sense it checks out all possible answers to the problem at the same time. If you need to find a classical computer, you want to find the shortest route to go from Delhi to Jalandhar, you can, via stopping at various other places on the way, a list of them, you just have to go through all the possible routes and find the shortest one. The quantum computer can cut that to smelling out all routes at the same time. So it's got a lot of interesting theoretical algorithms that if we had a quantum computer, we could do a number of interesting things with it. Yeah. The problem is we don't actually have one yet, but the topological materials provide one way that we might be able to avoid this problem of decoherence and preserve entanglement, which is why people are excited. Yeah.
Thank you, Professor Haldane. Yeah. Give a good round of applause, please.
Thank you.
Now, I request Dr. Rao to kindly conclude the session, please.
I'll take care.
Okay.
We appreciate very much the enthusiasm shown by the audience in interacting with the Nobel Laureate. I'm sure the Nobel Laureate will be available for further discussions. The Nobel Laureate, Professor Haldane, has made an outstanding presentation on quantum Hall effect. He also mentioned that we are now in a second quantum revolution. The practical use of quantum Hall effect, there will be great opportunities for the next few decades to come in the areas of quantum materials, universal quantum computing, and quantum computers. He has also mentioned that Microsoft has shown keen interest in developing qubits. Quantum Hall effect also has applications in quantum electronics and quantum information processors. Further, the Nobel Laureate has described how this is being used in satellite communications by a Chinese team of engineers. What I am trying to conclude is, for the youngsters present here, quantum Hall effect has a great promise, potential, and vast opportunities for many of you to work for the next several years. Thus, please explore the opportunities that are abundantly available, which were not available to some of us and to some of the people who are sitting in the audience. This is the great chance and opportunity for the youngsters. Let's give a big applause to the Nobel Laureate.
Thank you, Professor Rao. Thank you so much. Yeah. Thank you so much. May I now request Honorable Chancellor, lovely Professional University, Shri Ashok Mittal ji, to kindly felicitate the Nobel Laureate, Professor Duncan Haldane, and may I request Mrs. Haldane to join on the stage for the felicitation ceremony. Mrs. Haldane, please. Please. Somebody kindly escort. May I request Pro-Chancellor Madam, worthy Pro-Chancellor Madam to join on the stage, please. Give a good round of applause. Thank you, Professor Haldane, for being at LPU and sharing your words of wisdom and deep knowledge with students of LPU. Professor Haldane is receiving a medal which is conferred upon by the Indian Science Congress Association to all the Nobel laureates each year. I now request the Honorable Chancellor to kindly felicitate Professor D. Narayan Rao, the chair of this session, and the Vice Chancellor, SRM University. Kindly felicitate him. Sir, may I now request you to felicitate Mrs. Vijayalakshmi Saxena, the Secretary-elect, Indian Science Congress Association. She's the President-elect. I beg your pardon, she's the President-elect. Give a good round of applause. Thank you, Professor Haldane. Thank you, Mrs. Haldane. Thank you, Professor Rao. And thank you, Professor Saxena. Thank you, Honorable Chancellor. We are now heading towards our next event, the grand gala opening of Children's Science Congress. May I ask the Master of Ceremony, Dr. Sanjay Modi, for the Children's Science Congress to kindly be on stage and begin the proceedings. Thank you so very much.